And without further ado, I will present our speaker, whom I'm really happy to have, because it's been a while that we have been following this nice work, and now we have opportunity to listen to you. Floor is yours, Jean-Gabriel. Thanks for coming.
Hey, thank you very much for the invite. Super fun to be here. Yes, so I want to talk about today about low-dimensional embeddings of networks. It's a bit of a cheeky term. Low-dimensional is probably not even the right terms. It's probably even like ultra-low dimensional. Okay, and today my talk is really kind of a treat. This is one of my favorite comics from Belgium, France 8. La Fièvre d'Urbicante. It's a beautiful comics that's like about this growing little structure that kind of lands and finds its way into civilization out of nowhere, and it kind of like keeps on growing and becomes this thing that's like takes over city and the world. And it feels like a good analogy for like the models we have today in machine learning and networks that are super good and super large, very complex and kind of like beyond human comprehension. And I've had a lot of fun in the past year just contemplating these models and having fun with large language models, super big embedding models, and so on. But sometimes I also feel a little bit like, yelling at this from the distance and be like, oh, this is destroying the beautiful order of mathematics items we've been doing. And these theories, we're kind of losing track of them. They're becoming too complex, and we can't say much about them except that they work. And so today it's really like my goal is to go back to the origins. And so in this comic book, this big structure start out as this little cube. And that's going to be kind of my goal today, is like talk about these super simple models of networks that have the kernel of something really powerful in them, that are still useful and beautiful, and that we can do something with. And so these low-dimensional models of networks. And I'll get fairly mathematical at some points, but not too much. I don't want to lose you on Zoom. And so I'll just give you like a few pointers. What I mean really by these low-dimensional models of networks. I'm a probabilist, so I think of these things as probability distributions over networks. So there's a graph G, and then we have like some parameters. And when we say low-dimensional, is that like there's not too many parameters. So there's not like 1,000 parameters per node. So we're not talking about large embeddings. And then my focus in science has been in the past few years to do inferential frameworks. So I'm not so much interested about like how to define distribution over networks, but more kind of take the networks, feed them into some inference algorithm, and make conclusions about these probability distributions from observations. And so network science got started a long time ago. There's been like kind of modern eras, in the 2000s, where what we meant by low-dimensional model origins was something like, there was large patterns in the world, and this was this physics thinking that we'd like model these with, the salient patterns. We would have simple mechanisms. So everybody has heard about preferential attachment or like small worlds and so on. Those were kind of very simple, not machine learning explanations, just mechanism to describe patterns. But there was a even older history of doing these kind of low-dimensional explanation for networks in statistics and sociology. So there's beautiful literatures in the 70s, 80s, and so on, that were like literally ultra low dimensional models where the nodes of a network would have like locations in a space, and then the connections would be based on these nodes being similar. So that's kind of closer to the ideas of machine learning embeddings we have today. And these ideas were taken again by the physicists and machine learning folks kind of mid-2000s, 10s, with these hyperbolic models, where again we have a few explanatory variables, but the geometry is weird and lets us do kind of fun things. And to just like make a story short out of this, there's been quite a few recent kind of big piece reviews that say that like, hey, these geometry approach are like very good for networks, surprisingly good. They have like 2 dimensions and they happen to model the real world like super well. And then there's some caveats. So there's been interesting debates that say like, oh, there's kind of limitations to low dimensional embeddings, not for necessarily geometry. because of the kind of product structure that they have, and there's been kind of this battle that says like, oh, maybe we can, maybe we can't. It's still, I think, not fully settled. And so for today's talk, I want to talk about kind of two vignettes. So two things we've been working with in the lab in this space of low dimensional embeddings for networks. And the first one is this Bayesian approach to hyperbolic models. So I'm like starting super technical, but as a topic, but I'll try to make it fairly high level. So don't tune out whenever there's an hyperbolic model. I'm like, oh, not one another of those. That's going to be difficult, but it's actually the ideas involved are high level. And so this is joint work with Simon, who's a PhD student at Laval University, where I'm also affiliated with, and Antoine is a professor there. And so Simon has been leading a charge on this. Okay, so hyperbolic models review. Here's kind of like what you actually need to know to understand the ideas here. And so it's going to be a model of networks where here's the statement we make about how we observed the networks. We have a position in some hyperbolic space. So just a position for every node. And then there's a distant function that's like where the hyperbolicness of the space is kind of shoved. Okay, so that distance captures properties of the space, but just the idea, two nodes are close or far, that's what the distance is going to tell us. And then without going into too much detail about what the distance is, we want to make a probability model about the data. So what we do is we say that two nodes, I and j, are going to be connected with an edge represented by the adjacency matrix aij having entry 1 as an inverse logit of the distance. And so here, this distance, as it goes down, you can see that the probability of the edge kind of goes down. And then there's this beta parameters that control how steep the decrease is. And r is a typical distance. And once we have that, we need to, yeah, Liuba?
One question, because you are assuming some position of nodes in the hyperbolic space.
Yep.
And the reason for that is that your system, right, for some reason you are choosing this geometry of that. I mean, it's a very basic question, but just to kind of allow me to ask silly questions.
Yeah. I'm gonna get, I think, to like assuming the positions. For now, I'm gonna explain like how the model would generate networks, I suppose. So we would assume that like we're given positions, we're saying like, hey, there's this big space that's abstract, the nodes are at location in there. And then depending on their proximity in that space, that's gonna kind of determine edge probabilities.
Okay.
Mike?
Yeah, just to clarify, so as far as I understand, for the time being, you haven't made any assumptions about how points are distributed in your space,
yeah,
and what R is.
Yeah, so the points are just like at locations. They're like
yes, so they can be uniform. Well, as we know, as probably.
Yeah, exactly.
But it's no, depending on how you distribute them, the properties of the network is different. But okay, so you haven't assumed anything concrete so far. Okay.
Yeah, exactly. I'm not assuming anything concrete. You put the nodes everywhere in that plane, and kind of where you're going to put them are going to kind of change the probability distribution over the network. And so this distance, kind of when nodes are close, they get connected. That's what this inverse logit does. And then the probability of the network is obtained by kind of conditional independence. So every edge is drawn independently conditioned on the position, and that gives you kind of a network model. And okay, like why do we use these complex models? There's this beautiful review in Nature Review Physics recently by kind of a team that worked on this for many years. Is because like once you kind of assume this network geometry that's hyperbolic, you kind of get lots of properties of real networks for free. So this one is like a metabolic network of E. coli. And so like the nodes are kind of reactions or metabolites, and they have like position in this hyperbolic space. It's a 2D representation. They're not like spaces we can draw really easily. And you have things like nodes that are closer to the center in that space are kind of close to everything. And so they are connected to loads of nodes. and nodes that are in the circle around that space, they're kind of like in different sectors. And so, for example, this node is very far from that node, even if they're kind of close in the drawing here. And this kind of bending of distances allow us to represent that work. And the reason why we do this, the promise, like when people started doing this, is when that if you have like a real network, and the network I'm showing here is a network of trades. So it's like every node is a country, and an edge says that two countries have a commercial relationship. So if we have one of these networks, you find a position somehow. So like overall, the possible position that the nodes could be. So that's the fitting part. So you're embedding in that space. Then you'll kind of have like an efficient map of the world that will tell you something about it. So kind of a semantic space for nodes. And so here we can see that like the USA and China are very close. They're like big commercial partners. You have all the blocks of the world colored with different colors. So here we have like Japan and so on. So that's Asia. We have a European block, and that's kind of all found in an unsupervised manner by just putting the nodes and saying like from this model where the nodes would be. And in more details, what I mean by fitting, it's like there's various approaches to it. Here I'm showing the maximum likelihood or maximum posteriori explanation, where you have your probability model and you're asking like, what is the best of the probability model? And here the parameters theta is like positions, so where the nodes are, and also the shape of the connection function. And you can also do this in a Bayesian way, where you want to kind of sample the locations instead of finding the best one. Does that answer the questions we had about the model? Yeah. Okay.
Well, actually, I do have a question here, because here obviously it is a weighted network, or is it not?
A weighted, you said?
Is it a weighted network or not? And if
yes, so there's very like I'm looping kind of everything together. So this one was weighted. I showed also a bipartite that there's versions for directed, so we can kind of like change the model. So I mixed everything as figures. Here I'm going to talk about the specific versions of this real soon that's going to be unweighted, but it's kind of easy to change the details of the model to work with whatever kind of data you have. Yep. Okay. And so the problem that we're solving with this first kind of paper that we're working on is basically the fitting problem. It turns out to be quite a difficult optimization problem. There's a couple reasons. One of them is that it's like a rugged landscape. So solutions will kind of tend to be trapped. So if you do like gradient descent, that's kind of difficult. There's also a lot of symmetries. So there's small spaces, so you can kind of rotate the solution and get to the same kind of quality. Yeah, you can take blocks of nodes and move them around, and it's not going to like change the solution too much. And so that makes it kind of quite difficult to actually use kind of out of the box sampler that are like problem agnostic. So for example, I'm a Bayesian. I use Stan quite a lot, which is a probabilistic programming language that you like give it a probability model, and it's supposed to sample from the solution space, and it just kind of doesn't work out of the box because that's too hard. And the rugged landscape makes gradient descent quite difficult to apply to. And so the state that we are in, the state of the art for this problem, is like years of kind of small tricks compiled into a big heuristic routines. And so like if you read the papers, they have like 10 pages of algorithms where they're saying like, oh, this is the way to do it, and then they actually kind of make the problem, they revisit the solution and kind of add a bunch of tricks until it kind of works. And the result of this very complex work is that, okay, we have things that work very well, good performance, but they're kind of brittle. So you can change things about the graph and you'll get a very different solution, or you can kind of construct edge cases that make the algorithms break. And they're also all within the MLE perspective. So they're trying to find one solution. And so for this project, our goal was to kind of try to find a robust way that would kind of always work to sample from the space of solution. And so we want to be Bayesian, and we want to have a robust algorithm. And I want to be more precise here. So I've been kind of floating many versions of the hyperbolic model. I'm going to focus on a specific version that's called S1. And so in that model, it's undirected edges. The likelihood is conditionally independent, and the parameters are angles. So we have this circle, and we're just trying to place the node along the circle, and the distances are hyperbolic. Okay, and so to give you kind of two intuitions for why that's a difficult problem, I want to show you kind of two important things to know about this problem. So the first one is here I'm going to show the vertex position. So what I'm going to do is I will fix the location of all the nodes in my network and take one of the nodes and try to find its optimal position. So like an oracle gives you like the location of n-1 node, and then you're trying to find the embedding of the last one. And here we're showing the quality of that solution. And what would happen as you do this is you'll find that basically the likelihood will peak and go infinitely negative at a bunch of places. And specifically, it will do this when it overlaps with a different node. And because the model has this kind of barrier that says like you can't put two nodes at the same location. And the results of this is that like as you're trying to find an embedding, if you like move one node at random, kind of any local solver will encounter these barriers and will get stuck. And so if you start here, you can't move there without making long moves. So that's kind of a local barrier to optimization. Another feature of this algorithm, so in this one I'm showing now, I'm trying to like solve the location of every node at the same time. And I'm doing this on a network where I know the location. So it's like a fake network. I created the nodes, I know where they should go. And I'm showing this on the true angle axis. And then this is the estimated axis. Yes, Mike? I think there's a question by Mike.
Yeah. I'm sorry, I'm a little bit confused. Why exactly, where in the model comes this condition that two nodes cannot be at the same place?
It comes from if two nodes are not connected, the logistic will repel them.
But does it repel them infinitely? I mean, it seems.
Yes.
Well, it does.
So that's where that comes from, exactly. And so, okay, so the second intuition for why that's like a difficult problem. So we have the true angles here, right? So I'm like generating them. Somehow I use 10, which is this automatic sampler. And so I would have the true angle, and here I would have like whatever I estimate. And what 10 will do, it'll give you like a kind of rainbow like this. So every color is a different Markov chain. So I tried to sample the location. So I have like the pink chain, the orange chain, the blue chain, the dark chain. And what you will see is that like what you would want is to be on the diagonal, right? The true angle, you find the estimated angle up to a rotation. But what happens is that we like find kind of hints of the true solution. So I highlighted one in black here, right? So these nodes are kind of all correctly located, but they're wrong. They're like shifted a bit. Or these ones are all corrected, but they're flipped. Okay, so there's kind of this cluster structure to the problem where like clusters of nodes are easy to order, but then you kind of need to move them around. And so the approach we took in this paper is to do the merge split Markov chain Monte Carlo. So it's a method inspired by things that have been done for like the stochastic block models and so on. And the rough idea is that like instead of just moving nodes around, because these long moves are difficult, we're just going to move clusters around. So here's an example of what I mean for a cluster move. So here I have a like very small embedding. So the first step would be to find clusters. And we do this by having a gap T. That's a random variable, so that's an angle. And we say like, if there's a gap that's bigger than T, then we call that like a separation between clusters. And so here we would have found 5 clusters. Okay, and once we have these clusters, we pick one, for example. So we would draw here the blue cluster. And one of the moves we can do is just like flip this cluster around. So you can see that like the color of the nodes shifted. So what was on the right is now on the left and vice versa. And so that gives us like one way to move a lot of nodes at the same time. That kind of takes care of some of the imprecision that we find with Stan. And then you can stack a bunch of different moves so that you can exchange clusters. You can insert a cluster from one location to the next. And then to complete the chain, because clusters are not going to explore everything. We need to be able to adjust the moves. We stack on top a random walk where the nodes can walk a little bit, or you can do kind of local Hamiltonian Monte Carlo that works also. And the important thing is to have like the two, so cluster plus something else, and then a bunch of little bells and whistles to make sure that the problem works well. So we kind of need to disambiguate rotations so that a solution that's rotated can be kind of aligned back. And then a few kind of details about graph isomorphism needs to be taken care of also. And the result, when you stack all these things together, you have like a big Markov chain that's fairly efficient, and you go from this mess to something that's like perfect. So when we saw this, we're like happy. We basically solved the problem. Now we can sample perfectly, and you also see kind of one of the features of this new solution is that we have the location, but we also have like error bars now. So we can say the nodes is here, but there's a bit of wiggle room, and we quantify that with the Bayesian sampler. So I want to walk through a couple results. Maybe before that, I would just want to stop and see if there's any question about the sampling. Okay, so I want to show a couple of results about the sampler then. And so the first results, if you're kind of a Markov chain person, is that we have like this robust convergence. So these plots are showing like the sampler running for 20,000 iterations with a couple kind of configuration. So cluster MCMC in blue is the full thing that I just talked about. Random walk is if we don't have any of these random walk moves. And in kind of beige, dynamic HMC is STAN. So it's like out of the box sampling that doesn't have any clusters, but it is like very efficient otherwise. And what we show here, we're starting from a random location. So the chain starts at this little dark point, and it's like a very bad solution. It's just a random solution. And even if we start super far, we're able to converge to the true solution pretty fast, like within 1,000 iterations and so on. Whereas HMC, even given a super long time, doesn't go there. And if we start at the actual solution, we don't move away. And then there's this measure called R naught that's used, R hat, that's used in this field that basically says like how good of a mixing are you getting? And it's supposed to be close to 1. And so we get, 1.03, that's considered like good. So the chain is mixing well, and competing approaches get like, as high as 8 or 2, so they don't mix well. Another thing that we find is like if you look at the locations of 2 different nodes, because we are now probabilistic in our embeddings, we can look at the correlations of these embeddings. So here are 2 nodes I and J that are like close in the true network. So I generated a fake network with 2 nodes that are close, and then I embedded it back. And you can see that these locations have kind of high correlation, and that correlation is not a normal distribution. It's kind of a skewed Gaussian. So that's something you can't capture with like simple approximations. You can kind of do this figure for all the pairs of nodes and get like this kind of galaxy of embeddings. So here, every row is a node and every column is a different nodes, and you have like the joint embedding. So I like to look at this figure and like find weird things. So we have like bimodality, where like there's kind of 2 different solutions that are possible. And when we can see like very kind of strongly correlated for some of them are weakly correlated. So it's a very kind of complex post-area structure that you need to sample. You can't get away with just doing like variational inference or something like that. And the last thing I want to talk about with the sampling is that the other cool thing about having embeddings that are probabilistic instead of having a simple embedding is that we can have like error bars on all our network metrics. So here, those are the stretch, the hyperstretch, original, and the greedy are kind of all different ways that people in the hyperbolic embedding world have come up with, to quantify the quality of an embedding. So there's just, for the purpose of this talk, what's important, they're like kind of notions of quality that we can compute on an embedding. And in blue, this is Mercator. So this is kind of the state of the art in the field for finding embeddings. And then orange would be kind of the embeddings, the quality of these embeddings if we had known the position of the true graph. and then the blue is the posterior ones. And so we can see that basically the samples are giving us a description and now error bars around these true bars of the original graph. And Mercator, so this kind of maximum likelihood, is instead kind of overfitting and going like way off where the distribution is. And so that's kind of let's say like a cautionary tale that like if you optimize, you're gonna probably overfit and you're gonna miss this uncertainty that we actually have. The data is not really telling us what's the true value of the greedy stability per se. It's giving us a range, and we can now do that with the sampling. And so the takeaway for this kind of first projects that like if you need to remember something about those is that you can use these merge split ideas that have been like super popular in stochastic block models and so on for S1. And that will give you Markov chains over hyperbolic embeddings. And these samples, once you have them, you can do Bayesian things and compute uncertainty. And so that's kind of the two contribution: good sampling plus uncertainty. For folks that are interested in big data, that's like currently not in the big data regime. When we do this, we like do it with a couple hundreds nodes at most. And it's so there's opportunities to like make things fast. So that's a place where we're excited to go if you want to talk about that. And we also are exploring ideas about how to use these cluster moves within kind of insertion optimization routines. So these big stacks of brittle tricks, you can add hours on top, and it's going to make the stack even more efficient, if not a bit more brittle. And so we're excited about trying that out. Okay, I think I can take question on this part before I move on, if there's any.
There was a question in the chat.
Yep, by Mike first, and then.
Yes, man.
Okay, I can start.
Yeah. Sorry, I was muted. Basically, I wanted to ask to clarify what sort of your model, what is regulating the degree of nodes? Is there a special internal variable which regulates them?
Yeah, in the S1 model, there's basically a hidden variable for every node. And so location plus a variable for the degree. We also sampled that just normally with Stan on top.
Yeah, and this variable is just given at the very beginning, and you don't do anything with it.
Yeah, there's two. So we can for these results, I was fixing it to the true value. Just for the simplicity of the exposition.
Okay.
But we can also infer it. So we did that with the Gibbs sampling, where basically you find the angles, and then once you know the angles, you find the degree, and you alternate between the two.
Okay.
And that works pretty well.
Yeah, it is what I actually guessed from what you were talking about, but just wanted to make sure that I understand correctly. Thank you.
Okay. All right. So there's a question by Yasaman. Can we have embeddings of polarized networks or networks with multiple poles, or the method is hairball-like? So do you mean by this of like having like one group or like kind of two groups? I'm just asking a clarifying question here by what you mean by poles. If that's what you mean, then yes, there's kind of no restriction. The model is not very good. Like it doesn't. Well, no, that's not true. Actually, the model has this notion, can represent this notion of multiple poles by just basically having nodes kind of grouped in two locations around the circle. So you have like them on the left and the right, let's say, with a big gap between the two, you can embed it pretty well. And then there's a question by Tiago.
I'm trying to unmute Tiago, but I don't know why he cannot unmute.
Ah, okay. But he wrote, this is very nice. Is the algorithm slow because of the ON squared to all forces? So yes, there's a part of this. So we're exploring idea with negative samplings to make it fast, and also along the line of your subquadratic papers. I think that's going to be helping. But one of the bigger problems also is that you kind of need to solve a graph orbit problem in there because you want to kind of be able to align all the graph samples. And so if you have like two nodes that are isomorphic, you need to find that. And so there's like kind of very expensive post-processing. Otherwise, you wash out the signal because of the graph symmetries. So that's also one of the big bottlenecks. And yeah, the evidence, I don't know. It's going to be our hard integral. We've not gone there yet. Happy to chat more about this. Okay, I'm seeing time run, so I want to chat a little bit about a second project that's kind of related. And so this is idea of like, once you have the low dimensional embeddings, kind of what to do with them. And so this is a project that we completed last year with Alice Petania at UVM, and also Antoine again, who's been like the constant throughout these projects. And so for this, I want us to take a step back and kind of like just, re-go through the reviews of this kind of machine learning pipeline that's as old as time. And here the idea would be you take your graph and then you embed it. So now you have like points. They're in a Euclidean space or a hyperbolic space, doesn't matter really much. And like, why do we do this? Is that we can do a bunch of things to the embedding, right? We can, for example, cluster it and use one of the standard off-the-shelves approach to find the blocks and then lift them back into the network. And we now found something about the network. And it's very nice because it works for whatever input you have, right? There can be text, there can be graphs, and we have all them the same toolkit. And so that's been used for non-network stuff, but that's also been used for networks, and especially hyperbolic networks. So here you have like in the middle one, that's an embedding of a graph in a hyperbolic space. So there's all these poles we were talking about just a bit ago in the questions. And then you can apply kind of off-the-shelves clustering algorithms to find these blocks on the embedding. And the problem that we are trying to solve with the second project is that the state of the nation, kind of like the toolkits we have at the moment, there's a lot of focus on the embedding itself. Like I even talked about it just now, like a way to find better embeddings. And there's not much focus on the clustering step. And the reason why is that we have this fantastic battle-tested kind of set of heuristics that work just very well when the clusters are clear. If you'd go right now on like sklearn.clusters, you'll have like these 10 algorithms that everybody used, HGB scan, optics, and so on. They've been around for a long time, and they find clusters pretty well in like various situations. But despite this, there's been interest in network science for building custom tools, specifically for hyperbolic and kind of simple embeddings. So there's two nice papers that came out in the past 2-3 years. So the one on the left is like super fun. It was out of a 72 hours of science. So the paper was written in 72 hours and put on archive. It's quite good science. And what they're trying to do is this kind of old machine learning pipeline, right? Take the network, embed it, detect the communities by clustering, and then find a network of communities. And there's a nice PRL that's kind of applying this at scale and relating kind of what we find with hyperbolic embeddings to these more kind of traditional network detection method like Louvain and InfoMap. And so I was reading these papers and thinking, hey, that's quite cool. But I actually know from like reading my computer science textbooks that we can actually do better than whatever these heuristics were just for the specific case of networks. And so the goal is, the second part was really to find these even better clustering for one dimension. And so I'm going to tell you a bit about that soon, but I just want to put a bit of math to formalize what I mean here. And so we're going to make the problem a bit easier. We're going to ignore the hyperbolic embedding, and we're going to take the nodes and put them on a line. Okay, so there's no longer any circular boundary conditions. And so this linear orderings would be like nodes at the top are like 1, 2, and then they're ordered all the way down, and then you have a way to put them on this line. Okay. And then the goal is to split these lines, these nodes into contiguous layers. Okay, so all nodes, we want to find these little lines, and we're going to call them our communities. So that's the clustering problem in 1D, linear clustering. And the way we are going to do this problem, we'll treat this as a discrete optimization. So we'll have a quality Q. That's the sum of the quality of a bunch of layers. And we're going to find the split in layer that maximizes this quality. And the objective functions could be, a likelihood, if you want to be probabilistic about it, but if you want to sin, it could be like a modularity or kind of a balance cut or anything. It really doesn't matter. Just it's a function that tells you how much you like the split. Typically, it will penalize having edges between clusters and favor dense clusters or something like that. And then the solution, the intuition for why we can do this very fast is that basically the problem is very weakly interacting. So your optimal clustering of like what's happening at the top of the network is kind of independent of the optimal way to cluster the bottom of the network. So parts of the solution don't need to talk to one another. And when that's true, computer science tells us that we can solve this very effectively with dynamic programming. Okay, so here's the main insight of like how to set up this as a dynamic programming insight. We can basically set up the problem in a recursive way because of this additivity. Okay, so here's what I mean. Assume you already knew how to partition all the subgraph of this like very little graph. So if I give you only the top one node, you would know how to partition it. You would say like, hey, that node is alone. If I give you the top two nodes, you have like an optimal clustering according to your objective. The top three nodes, you have a different optimal way to partition it, and so on. So you know all the ways to partition the subgraphs. Then you want to recurse. So you want to ask the question, if I add one node at the bottom of my embedding, how do I extend my solution? Okay. And the answer is you want to solve this maximization problem. So you want to solve the quality of the top J node is going to be a maximization over the quality of the top K minus one node plus a last layer for all choices of layer. So you're basically looking through all these new partial solutions to compute the best solutions to 5-1. So you're exploring these linear number of new clustering. And that's very easy to do, this computing, right? It's like linear number of clustering to extend your solution. And then you're done. You now know how to compute the top 5 nodes, and you can extend that and then use that solution to compute the top 6 nodes and so on. And so you recurse all the way to the full network, and you now have a way to split your network. So there's more details in this proceeding of the Royal Society paper if you want to walk through the algorithm, but doing this turns out to be optimal. So like if I'm going to go through results, I just want to flash right now that like this is super fast. So the dynamic programming solution is in orange, and like all the black curves are a bunch of heuristics that like one might reasonably come up with. And as the running time is a function of kind of network size. And you can see that the orange curve is basically at the bottom. There's a single curve that beats it, and it's like the pure greedy solution, but the pure greedy solution is like so bad that you don't really want to use it. Okay, I think I want to take questions and then I will go quickly through the results. If there's none, happy to move on. Okay. Oh, and by the way, Liuba, my phone died, so I can't keep track of time. So do tell me.
Perfect, but that's what is a nice seminar is about, that people forget about time.
Okay, all right. Well, I just have
anyway,
results for
we're about kind of to wrap up if you can, and then we can go forward.
Okay. Right, so I want to show a few results about this new dynamic programming, and then that's basically what I'll have for today. And so, okay, here's what it actually behaves like if you fit it to real networks. So here I have a network that I created. Basically, I have a linear ordering where nodes are correlated with the community structure. So you have like a yellow cluster at the top, a green cluster in the middle, a blue cluster at the bottom, a purple cluster, and you should be able to find this by clustering linearly with, say, the modularity. And so we apply the dynamical program, and we find 7 layers. The quality is like 0.49. It's going to matter, so that's why I'm putting the number. And then there's like a few extra layers that are handling a bit of noise in the structure, and that's fine. If you do pure greedy, so like this kind of solution where you just find the best cluster for nodes and you try to merge layers, but as soon as you can't, you stop, you get this solution that has like 476 layers. So absolutely garbage. And modularity close to 0. But then you can start using kind of what people have been using before, which were like pretty good heuristics, where you would merge layers, you would accept that you're making errors in the way, but then you would overcome these mistakes and choose the best solution you saw along the way. And so these merge heuristics give you pretty good solutions. But if you look at the quality, they're slightly lower, right? So 0.49 versus 0.48. And they have fewer layers. So if I were asked to say which solution is the best visually, I would choose the merge heuristic. It like kind of looks better, but the quality is lower. And so here, the point is that like these heuristics are hiding problems about the objective function like modularity. Like we can't maximize fully, and so we're seeing like this lack of finding more layers that modularity would have. So by improving the clustering, we can actually reveal problems. Here's a even worse case where like the ground truth is now super noisy. So if you do optimization, you'll find a bunch of layers, and that's true, that's the best solution. And like these kind of merge or critical gap methods will find way fewer layers, but that's actually a pretty crappy solution. It's within 20% of the optimum. Okay, real quick, once we know how to cluster these layers, it turns out we can actually cluster circular embeddings without any problem. We can just take a linear solution and kind of turn it into a circle. So the algorithm works on this too. And then here's another thing that you can do once you have a super good clustering algorithm. You can basically ask, is embedding actually a good idea at all? If your goal is to find communities. And so here what I'm showing is like a collection of 200 networks, and we're gonna see the quality of what we find with embedding as divided by the quality of what we would find without embedding. So like, Gervin Newman or the fast unfolding algorithm that's trying to maximize modularity. And so ratio of 1 tells you that embedding did as well as these direct methods. And a ratio of above 1 says that you did better. So that like embedding helped. And that's basically what you get. Like embedding never helps. It always does at best as well as direct optimization. And before we had the dynamic programming, so if you were kind of using one of these off-the-shelf method, we were actually pretty far from optimality. Like no network were we able to like do as well as direct optimization. And now like we solved clustering, right? There's no more clustering errors, and we're still not able to overdo it. But now we can't blame the clustering because the clustering is now done literally optimally. You can't do better. And so that's kind of the things we've been thinking about in this space. I want to say one last thing is that like once you know how to do these clustering, you can kind of like apply them everywhere. The ranking can be hyperbolic, but it can also be something like spring rank or like Bradley-Terry. You can use covariates to rank your nodes and cluster them along like age layers, or kind of any centrality measure you can think of will give you a ranking of the nodes. And so you can kind of now use this algorithm to split the nodes in this way. Okay. And so my takeaways here, right, is that like now we have this optimal clustering of 1D embeddings that we can do. It's literally not more costly than anything else. Like there's proofs in the papers where we're showing that like the existing heuristics are actually as expensive as doing it right. So there's no reason not to do it right. And sweating these small details can give you pretty interesting different solutions. There's a GitHub link here. So we called it Divider. So we did our best to have like a pretty understandable package. It's all in Python, so not super fast, but it still works. And there's tutorials, so you can kind of try it out for yourself with your algorithms and your data. And now that we've solved that, there's kind of exciting opportunities. Now that we have the clustering problem solved, we might ask like, can we do better? Can we do better embeddings without the interference of the clustering to kind of detect communities even better? Or can we go beyond one dimension? Can we use the ideas of dynamic programming to work in 2D? So far, hasn't worked for us, but I'd be interested to hear your ideas. Okay, so that was my kind of like yelling at big models and focusing on simple model talk. one-dimensional models, they can still teach us something about networks. We can find these little clusters and we can find them fast. That's been a lot of fun. And these models are the kernels of more complex things, right? Like these 1D clustering now, maybe we can use them on more complex data. And same thing for S1, like people have been moving to larger and larger dimensions in hyperbolic planes. And they've been finding interesting clustering of real data with this. And so it's important to understand the simpler ones before we do that. With this, I want to thank the teams, and I'll be happy to take some questions.